All right. Thank you very much, Steve. The floor is yours.
Thank you, Mr. Chairman. Thank you, members, at least one member of the committee at this point, members hopefully soon. I'm here today to tell you about the Georgia aerospace industry and some good news about that industry. I want to start out by telling you a little bit about my center. We're the Center of Innovation for Aerospace. Our job is to work with the aerospace industry throughout the state to help them to create jobs. We do this by connecting them with resources throughout the state to help them be more successful, and I'll talk a little bit about that in a few minutes. There are actually 6 different centers of innovation around the key industries that were selected by the Commission for a New Georgia. We're just one. Agriculture, energy, life sciences, manufacturing, and logistics are our other brethren in the Centers of Innovation concept, and we work very closely with the other centers. So let's talk about aerospace. We have good news in aerospace. We are creating jobs in Georgia in aerospace. Jobs in Georgia are up 4.5% since 2006. So we won't get the 2010 data till later in the year, but it'll continue to go up. We're ranked number 5 among U.S. states in total aerospace employment. We have over 84,000 Georgians with an annual payroll of over $5.2 billion. And the other piece of good news is that the average aerospace worker in Georgia makes just over $61,000 a year, which is 43% higher than the average for the state. So not only are we creating jobs, we're creating high-paying, high-technology jobs. There are over 500 companies throughout the state. You see the map there on the right. They're not just in Metro Atlanta. We have companies in Metro Atlanta, Middle Georgia, North Georgia, South Georgia, Albany, Columbus, Valdosta, Brunswick, Savannah, Augusta, Cartersville, you name it, we probably have an aerospace company there. If not in every district in the state, we have people at least work for an aerospace concern, probably in just about every district in the state. So we have a very diverse, a very large industry, and it's really 3 sectors make it up: aerospace manufacturing, maintenance, repair, and overhaul of aerospace systems, and air transportation. So I'm going to say a little bit about all 3 of those. Aerospace manufacturing, we just got new data in last night at 5:30, so I had to update the briefing. We've moved up 1 place. We are now in 2010 ranked number 7 among U.S. states in aerospace manufacturing. Our exports have up 89% over the last 5 years, and in 2010 our exports were up 23% over the previous year, taking us up to $4.1 billion of exports in this state. And further, to put that in perspective, 10 years ago in 2001, our aerospace exports from Georgia were just under $800 million. So our exports over a decade have quadrupled. So we are really moving up the ladder. And the difference between number 7 and number 4, which is Florida, is only $220 million. So if we continue anywhere near the trend that we've been having over the last few years, we can certainly expect to move up again when the 2011 data comes out next year. And we have all the leading manufacturers. You see there: Boeing, Cessna, Gulfstream, Lockheed Martin, all the big guys. Maul, General Aviation Company down South Georgia. Tiger, Thrush down South Georgia. Triumph, which used to be Vought down in Milledgeville. So we have companies scattered throughout the state doing aerospace manufacturing. Our second key area is maintenance, repair, and overhaul. These 3 areas, our 84,000 folks, are distributed roughly a third in each area. As I tell folks, you build the aircraft once. You maintain it for the next 20 to 30 years. We're very strong in maintenance, repair, and overhaul. We're ranked number 7 among U.S. states there, with just under 14,000 employees working on civilian aircraft with an economic impact of $1.7 billion. On the military side, we have Warner Robins Air Logistics Center. It's the largest industrial complex in Georgia. They have over 13,000 civilian employees working on their military aircraft down there, and that has an economic impact of that area of $4.1 billion. So we have a lot of MRO activity going on in the state. Air transportation, of course, when it comes to airports, we're ranked number 1 in the world, the busiest passenger airport in the world, with a $32 billion per year economic impact. We also, in addition to that airport, we do have 104 public and 339 private airports throughout the state supporting not just the aerospace industry, but all the economic activities going on in the state. Lots of corporations come here because we do have good air transportation infrastructure. And because of that, we are the headquarters for some major airlines. Delta Airlines, which is the largest aerospace employer and I think the largest private employer in the state of Georgia. Atlantic Southeast Airlines, a major regional airline. World Airways is in Peachtree City, Georgia. UPS, which is on the north side of town. But they're more than just little brown trucks. They have airplanes, too. If you counted the airplanes, they'd be the 7th or 8th largest airline in the world. And we're a major hub for AirTran Airways, which is being acquired by Southwest Airlines. So we have a lot of activity there. So we've had tremendous growth over the past 10 years, especially in the last 5 years, 89%. So will that keep going? And the answer is yes. In 2010, we had a lot of major announcements. Lockheed Martin is adding 1,000 jobs as they double production of the C-130 in Marietta, Georgia. Gulfstream Aerospace announced a $500 million expansion in Savannah, which will add approximately 1,000 jobs there as well. Robins Air Force Base in Warner Robins is adding 500 to 800 jobs right now to support Air Force programs. Timco in Macon is hiring to support a new Boeing 767 maintenance contracts that they have there. Bombardier, which is our newest entrant last year into Macon, is hiring for their regional aircraft maintenance programs, and this is just the very top of the pyramid. We have companies all over the state that are hiring folks. Our biggest problem in this state is we don't have enough people to fill all the jobs that these companies have. And they're out recruiting all over the state and other states that are losing jobs and losing exports, and we're growing like crazy here in Georgia. So that's good news for the state of Georgia. So let's talk about what we do in the Center of Innovation for Aerospace to keep that going. We really connect industry to Georgia resources. We connect them to the technology we have through Georgia Tech, the aerospace research that goes on there. We're #1 in the country in aerospace research, not MIT. Georgia Tech is #1 in aerospace research in the United States, and their Enterprise Innovation Institute. Also, Middle Georgia College has an Applied Aerospace Research Institute in Eastman, Georgia, to support our aerospace industry. Mercer Engineering Research Center. The Hertie Foundation, which does works in aerospace fabrics and biofuels. The Georgia Research Alliance. So we have a lot of research capacity that we use to support our industry. We also work with our industry to connect them with the programs we have to get people. I said that our biggest problem right now is people. We connect industry with the universities. Georgia Tech is the largest aerospace engineering program in the country. It's double the size of the #2 program. We have 1,300 students majoring in aerospace engineering right now at Georgia Tech. Middle Georgia College, we have 500 students there, studying everything from pilot training to aircraft maintenance, aircraft structures, to air traffic management. It's the #1 air traffic management school in the country in Eastman, Georgia. Most people don't know that. We also have Southern Polytechnic. We have our technical college system. We have 6 FAA-approved training programs in those schools. We work with the Quick Start folks to get that training to our industry. We also work with Georgia Work Ready, the Middle Georgia Work Ready Aerospace Partnership. Amy Hudnall, raise your hand, Amy, is my associate director, a key member of the team that put that together and continues to keep that funded through grants. So we have a workforce ready for the companies down there, and the Chattahoochee Valley Aerospace Partnership. The other thing is we do partnership. We work with companies and organizations one-on-one through innovation projects, and I'll say a little more about that in a moment. We have cooperative agreements. We have a cooperative research and development agreement with Robins Air Force Base that allows us to work with them to connect them with Georgia resources. We have our intelligence, surveillance, and reconnaissance consortium that we formed with them to help them support the activities there. We have various technology working groups and unmanned aerial systems, biofuels and space. We have various advisory groups. We serve on national and international committees. We do a lot of business-to-business connections, connecting large businesses with small businesses when they're looking for a subcontractor, the small businesses with our large businesses. And we do a lot of connections with companies to make them more competitive. And their industry database, the data you saw today, we keep track of that so we know what's happening in our industry in the state. Our innovation projects, that's where we roll up our sleeves and we work one-on-one with a company to help them develop a new product or service that they can go out and sell and create jobs in this state. We connect them to the Georgia resources, and these projects, we work with small companies, work with the very large companies, and everything in between. So we work with all the industry across Georgia. We also have a matching grant program through the One Georgia Authority where we can give grants of up to $100,000. They're matching 50% by the company, 50% through the grant, and it's managed through a university system unit, usually through Georgia Tech or Middle Georgia for us. And the pictures on the right are a couple examples. I'll go over quickly. The top picture is the NASA James Webb Space Telescope that will be launched in the next 18 months or so to replace the Hubble Space Telescope. Major parts for that are being built at Middle Georgia College in Eastman, Georgia by the staff and students, and we used a grant to help offset some of that. Thrush Aircraft down in Albany, Georgia is flight testing a new airplane. We have a cooperative program between Thrush and Middle Georgia College so that they can get that aircraft flight tested, and that'll create 15 to 17 jobs in Albany when that airplane becomes certified. That is an agricultural spraying aircraft. That actually, they're looking at taking some of those airplanes, making them counterinsurgency aircraft now in the Middle East. The Georgia Consortium for ISR Sustainment, the base in Warner Robins has the responsibility for sustainment of the U-2, the top picture, the Predator, the middle picture, and the Global Hawk, the bottom picture. And so we're working with the base there to have an expanded technical interchange between the base and our Georgia research universities, colleges, and technical colleges. And really what we want to do is to get more Georgia companies up to speed on the technology required to be able to compete for the contracts that the base lets to take care of these platforms. Last year, the base contracted $5.5 billion worth of services and goods. We only keep roughly around 10% of that in the state of Georgia. We want to make our local businesses more competitive so they can win more of those contracts, keep more of that money in the state. Unmanned autonomous systems. We have a working group in that. We have a lot of activity going on in the state. We have the military folks here. We have all the armed services here. They're all using these kinds of vehicles, both air and ground vehicles. But there's a lot of civil uses that are emerging for public safety and agriculture, which, of course, we're a very strong state in that. So there's a match made in heaven for us to keep working in this area. We have Georgia Tech, which is doing a lot of research and development in unmanned systems. We have our Warner Robins Air Logistics Center ISR Consortium. We have our Middle Georgia UAS Development and Testing Center that we're putting in Eastman, Georgia to support our activities going on in the state by our companies. And the picture on the bottom, and Mr. Nick Alley, we'll talk about that in just a moment, one of our billboards for our capability in the state, the NASA ESTOL program, and he'll cover that in a little more detail. Biofuels for aerospace. When I came in, one of the things I learned from our Center of Innovation for Energy is that we are going to be a leader in biofuels simply because we have more biomass available than almost any other state in the United States. We have very little federal land. We have a lot of commercially available biomass. Read that as pine trees and other cellulose. And so if we can turn that into jet fuel, we can have a tremendous impact both on our environment but on our pocketbook. It's green in two ways. The example I give you is that in Atlanta Airport, we use 1.6 billion gallons of jet fuel a year at Atlanta Airport. That's approximately $4 billion that those airlines send out of state to buy their fuel. What if we used our biomass resources here in the state, we put that into factories throughout the state to convert that into jet fuel, and instead of that $4 billion going to Louisiana or Saudi Arabia or whoever, it went to South Georgia, North Georgia, and everywhere in between to our farmers, our loggers, our folks running our own areas. Tremendous economic impact. So it's green, both for the economy but for the pocketbook as well. And we're serving, Amy Hudnall is leading our effort in that. And we're serving in all the national committees on that. It's not going to happen next year, maybe not the year after that, but it is coming, and we want to make sure we're on the forefront of that. Our space working group, our newest one, the industry came to us and said, we want to look at space. NASA has changed direction. They are now going to go commercial. They're going to go out and contract for commercial services to take cargo and various things to the space station. So how can we in Georgia then get on that bandwagon and expand our space infrastructure and space sector in Georgia? And we're working with the industry to look at that, how we can do that. Things like suborbital space tourism and nano-satellite markets, very, very small satellites, maybe a foot in diameter. We also founded in the last year the Georgia Aerospace Advisory Council. If some of you came by the aerospace luncheon breakfast 2 weeks ago over in the Capitol, you met with some of those folks. We put this together to serve as a committee to advise my center on things we should be doing to help the industry in the state. We've been working with them since September. We had the breakfast 2 weeks ago. We have a big meeting planned for the spring of 2011 and looking at a Georgia Aerospace Summit in the fall of 2010. This is going very well. It's connecting our industry with our state activities to a much higher level than we've had in the past. So that is what we're doing in the state. That's good news. We are growing. We are growing fast. We are getting bigger. We are a national and international player in the aerospace market. One thing I forgot to mention, our aerospace exports of $4.1 billion are bigger than the aerospace exports of Russia, China, and Japan. We are an international player in this. Aerospace is becoming a bigger and bigger part of the economy of Georgia, and we're working hard to grow it and to expand the jobs in Georgia. So I'm ready for any questions you would have at this time.
Thank you very much. Questions?
That's called tankering in the business, and usually you would do that if there's a big difference in the fuel cost between one location and another. And Atlanta is one of those places that has a slightly lower fuel cost because of the direct pipelines we have from the Gulf into the Atlanta airport. So there's not a lot of tankering that aircraft that come in empty here. More than not, the aircraft carry fuel out of Atlanta to the more remote locations. Well, most of the time you don't like the tanker too much on fuel because it does affect the aircraft performance to carry overloads in fuel. But if we have biofuel, that'll help us quite a bit in keeping those dollars here in the state.
Any other questions? Well, I could have 100, I think, on this. You mentioned biofuel last, so I'll ask that. About 5 years ago, Georgia Tech was pushing for enzymes to transfer, in some way, change the structure so that they would get ethanol out of switchgrass and pines and that kind of thing. What are you using primarily? You mentioned pine, but how do you get biofuel out of pine?
Amy is my expert on that. I might ask her to answer that. They're using enzyme and other chemical-based systems to be able to take any type of cellulose.
Well, has that been a flop? Because I saw where
well, they're having a lot of problems with that. There's several processes. What you're talking about, the switchgrass and woody waste products and that kind of thing, going to ethanol has been very difficult. The biggest issue, I think, in overall biofuels is finding a method that you can actually produce and scale up enough to get the cost down so that it's attractive at all to the industry. That's the biggest issue that happened. But right now, they're not able to do it without a lot of subsidies. So.
Yeah. And that brings up two other questions. One is recently there's been a lot of information written by the people that maintain vehicles and are saying that the ethanol in the vehicles is causing a lot of maintenance problems over time. Yes, sir.
Is it ethanol in the vehicle or ethanol in
but it's also playing havoc in automobiles.
You know, what we're looking at on the biofuels front is processes that we won't use ethanol in aircraft because it will have issues with the aircraft systems. We're looking at processes, and we've not gone to one single process. We're looking at all of them that will take us to a jet fuel that looks and acts just like Jet A that they use now. Chemically, the same, will pass the same criteria and standards, because you can't have an airplane that's filling up in Atlanta with a mix of some sort of fuel and then going to New York and getting a whole different kind of fuel. We need something that looks exactly the same.
So those are called drop-in fuels, that they act the same as pipeline or an aircraft. And what you're speaking about is that they're taking, there are several processes where they're taking ethanol and then they have an additional process to make it into aviation fuel. Those are issues. They just had an announcement that Keeler is coming to the state. Range is closed for the time being. Keeler is coming in, has a new Department of Energy grant. And there's several other companies within the state that have pieces of the biofuel. And our working group is kind of concentrating on, we have the biggest user, Delta, a million
Billion.
gallons a year. Delta uses at Hartsville. We have the testing facilities at Georgia Tech and at Middle Georgia College. We have engine producers here, so we have a lot of the stakeholders in that industry. We have the infrastructure. We don't have any money, but we've got the infrastructure that we can utilize and test those. So that has made us attractive to some of the national groups.
Well, locally, we have some people who've developed their own methodologies for using biofuel in terms of animal fat to run their diesel trucks and things like that. A friend of mine owns American Foods, I guess, all the dog food and so forth up in Forsyth County, and he's learned that when you're rendering chicken fat, you can run that in your diesel trucks without too much trouble. So, works. Thank you, sir. And now we'll move on over to Nick. And as I said before, Nick, I've been flying remote vehicles now for about 40 years or more, so I'm very interested in what you have to say.
Well, you'll like this, because that's how I got my start. I started flying when I was 11 years old, and made a career out of it. So that really was the inspiration. That's what got me started. Thank you, Mr. Chairman, members of the committee. My name is Dr. Nicholas Alley. I am a transplant to Georgia from the West. Moved out here from the Idaho National Laboratory. Took a research faculty position at Georgia Tech back in 2007. And at the end of 2008, beginning of 2009, my current business partner lured me away from Georgia Tech to come to Aerotonomy Incorporated. And we're a small research company, and really the reason we do what we do is because we love flying, and we love all things that fly. In particular, unmanned aircraft or drones, call them UAVs, UAS, unmanned aerial vehicles, unmanned aerial systems. If you hear me use those acronyms, they're all airplanes. So our mission, what we do, has to deal with pretty much all systems, all UAV type systems, designing not only aircraft but designing their avionics, designing their structures, aerodynamics, and also designing and testing advanced aerodynamic technologies.
Before you go further,
Sure.
you want these back? Can we keep
No, you can keep those. Just so you know, I had to sanitize the slides that you have, so there are some things that I'm not allowed to release publicly yet, or we're not, for strategic reasons, we've decided not to release publicly. So there'll be some blank spots in your slides, and there'll actually be some slides that have been completely removed, so the slideshow won't follow exactly what you have there. I apologize for that discrepancy. But what's that?
This will be on the internet.
These will?
The archive will be.
Oh, it's, the discussion is, but the slides won't, will they?
The slides will be out there, won't they?
Whatever information you send us, we can archive and have that with the presentation, or that presentation.
Okay. That's fine, but this presentation right now isn't being recorded, right?
Well, this meeting,
The meeting is fine. That's fine.
but I mean, unless you can see, like you said, unless you can
Yeah. Yeah, from what I understood, this is what's going to be archived here. Yeah, okay. That's fine. That's fine. So to get started, Air Autonomy has been in business since 2004. We have received over 30 government and private sector contracts. Much of what we do is research for the Department of Defense, Army, Air Force, Navy, and I've put a couple slides together to show you our current research thrusts. Our first is shown here as a project that we're working on with the Navy, which we call AUDSA. It's an autonomous detect, sense, and avoid system. And one of the things with drones, and this is something that this committee should really be aware of, is that these unmanned aircraft, the FAA will not allow to fly in the national airspace. They have to fly in restricted military zones, or you have to go through a massive amount of paperwork to allow that aircraft to fly in the national airspace. I can't just go out to McCollum and put my airplane on the runway and take off. I can't even go to some field and put my autonomous airplane on the runway and take off. And the reason is that most of these autonomous aircraft don't have the ability to see and avoid other aircraft like a human pilot would. So we've been heavily involved for many years now in developing systems. This current work that we're doing, we're partnered with Georgia Tech. They're performing a lot of the flight tests of the system, but we're developing a system that can actually sense other aircraft. We have sensors, and then we also interface with current systems that are available to general aviation, such as ADS-B and TCAS, to sense other general aviation aircraft or commercial aircraft, and then we've developed algorithms that will cause an unmanned aircraft to avoid those oncoming, intruding aircraft. And that's a very hot topic now, research topic in all areas with the FAA, and right now we are working with the FAA and major UAV airframers to grow this technology and to test it. We do a lot of work with avionics, with autopilot systems. This is work that we did for NASA to test the ability for an autopilot to continue to fly an airplane after it's been damaged. Let's say it had a wing blown off or a tail blown off, something of that nature. NASA had a large push, a research push, to develop autopilot avionics systems that could adapt to any damage or inertial changes to an aircraft. And we actually developed a series of test beds which could simulate aircraft damage. And NASA partners send us their algorithms, and we would go fly those algorithms to see how well, when we simulated damage, how well the autopilot could overcome that damage. And to do that, we took these are quarter scale Cessna 182s that we put different modifications on, as you can see. Actually, let's see if mouse comes up here. You can see here this is a ballast tank that actually shifts forward and backwards. We call it our CG shifter, so we can move that. You're an RC pilot, so you know the phrase tail heavy plane won't fly or won't fly or will crash or won't fly at all, and then a nose heavy plane won't fly well. Well, this is literally meant to in flight make the airplane tail heavy, and then there's a ballast in there that we can burst if the airplane becomes too unstable. And then the top left is a wing that we designed and built that we can actually blow off the outer 30% of the wing in flight. So you'll have a large wing on one side and a small wing on the other. And then the far right is a wing that we designed that can emulate what's called aeroelastic twist. All airplanes, their structures will twist somewhat, and if the structure is weak enough, you can actually get to the point where your pilot would try to turn the plane to the left, and the plane would go to the right. And we've developed a wing that can actually simulate that behavior in a manner that once the behavior occurs, if the autopilot can't overcome that, we can recover it. We have another system that's called Synapse, a small image-aided path planning navigation system. This is for the Army. And this is, again, we're partnered with Georgia Tech, Eric Johnson and his UAV lab, to test this. This is more of a system that allows a UAV to fly in an urban environment. Imagine a UAV flying down Peachtree Street in downtown Atlanta, being able to sense the buildings around it and avoid those buildings. The AUDSA system was more for detecting other aircraft when it was out flying in the free airspace. This is for flying in urban environments. We spent a lot of our IR&D money to develop the aircraft that you see there in the top right-hand corner. That's what we call the Nanos, and it's what we call a micro UAV. Has 2 small cameras mounted in the wings, and we hope in the future to be able to transition the Synapse algorithms into the Nanos and use those cameras for this obstacle avoidance. The primary reason that I'm here today is to talk about our ESTOL program that we have with NASA. ESTOL stands for Extreme Short Takeoff and Landing. This is a project that we've been working on for the last 2.5 years. It was funded under a NASA STTR grant, or SBIR grant, which is a Small Business Innovation Research grant. And the purpose of this project was to look at technologies that could enable a transport aircraft, such as, say, a Boeing 737, to have extreme short takeoff and landing capabilities without having huge drag penalties. For those of you who are at all familiar with aviation, like Mall down in southern Georgia, they have a great airplane. It can take off in about 200 feet. But the problem with that airplane is that it doesn't cruise very efficiently. You can't go relatively very fast with it. The reason is the Mall aircraft was designed to be a short takeoff and landing aircraft, not to be this long-distance cruising aircraft. Cessna, or say a Boeing 737, on the other hand, was designed to be a long-haul cruise type aircraft, and it doesn't take off in a short distance. It's going to take off in 3,000 to 4,000 feet instead of 100 feet. Problem with that is that you can't operate a Boeing 737 out of smaller airports because of that. And the challenge that NASA came to us with was to look at technologies that could enable an aircraft to take off in extremely short distances, but at the same time have those technologies be able to retract or disappear so that you don't pay huge drag penalties, or you can cruise efficiently as well. And what we did was we designed, as part of this project, we designed a platform which we call our our ESTOL UAV, which is able to look at is able to compare directly the performance between conventional high-lift technologies and advanced high-lift technologies, which we call these advanced high-lift technologies, CETA technologies, which that stands for cruise-efficient, ESTOL-capable transport aircraft technologies. And you'll also hear me describe them as combined circulation control technologies. These high-lift technologies are threefold. We have one. The first is called circulation control, and I'll explain these to you so you don't have to pay too much attention. We have leading edge blowing and then over-the-wing powered lift. And you see a close-up CAD model of the wing on this UAV. You can see that the engines are mounted above, and you can see kind of an odd flap structure, the inner portion here, and I'll describe all that to you. So the first is circulation control. Now, circulation control has been was discovered many, many years ago by a guy named Henry Kawanda. It's well known for its ability to generate huge amounts of lift, massive amounts of lift. Just to give you guys an idea, when being able to generate lift directly equates to being able to take off in shorter distances, directly equates to being able to fly slower. And what this is for circulation control, we put a blunt or rounded trailing edge on the picture that you have here is an airfoil cross-section of a wing. So if we took a slice of a wing and we looked at the shape of that wing, that's what we'd be looking at. And in circulation control airfoil, we would actually blunt, instead of having a sharp trailing edge, we would blunt that trailing edge and we'd put a little jet slot on that trailing edge. So we'd pressurize air and we'd blow it out over the trailing edge. And you can see that right here. And because of that rounded trailing edge, we can actually generate massive amounts more lift than you can with a conventional airfoil with a conventional flap So that's what we call circulation control. We can blow out the trailing edge and increase or decrease the lift based on that blowing. And this is a virtual wind tunnel model, kind of showing the streamlined flow of air around an airfoil with a dual radius circulation control flap. Excuse me, I actually skipped one slide first. The problem that we have with the circulation control airfoil is that if you have a blunt trailing edge, you have massive amounts of drag. Sharp trailing edge, little drag, blunt trailing edge, large amounts of drag. Now, Bob Engler at Georgia Tech came up with what was called the dual radius flap. That dual radius flap can be retracted in flight, so you have a semi-sharp trailing edge, but then you can deflect that down, and it has a curved upper surface so that you can have that circulation control Coanda surface and blow out over it and get your high amounts of drag. So what we did, and if you can see here, this is a CFD model, or a virtual wind tunnel model that we run, a computational fluid dynamics model. You can see without blowing, you can see the flow separating. This is really large amounts of drag, but then we turn on the jet here at the trailing edge, and you can see what happens. You can see how those streamlines twist up and around like that. That is showing us that there's very high amounts of lift being generated, much higher amounts of lift than you could generate with a conventional airfoil.
Question.
Yes.
How does this vary from the Fowler flap?
Fowler flap is doing a very similar thing in that it's trying to generate more lift. A Fowler flap you can typically get, just to give you an idea, a Fowler flap would have, there would actually be, instead of there being a continuous flap airfoil section here, you would actually have a slot right here. You can see that where I'm drawing on the mouse. And that the air would be accelerated from the lower surface up to the upper surface of the flap, and energize that flap that way, and it would end up, Fowler flaps are an excellent way to generate good amounts of lift, but your maximum lift coefficient on a Fowler flap is typically about 2.5. That's about as high as you can get. You can get higher with multi-elements, up to 3.2 or so. And lift coefficient is the maximum amount of lift that you can generate. The maximum amount of lift that you can generate on a circulation control flap, a dual radius flap, in wind tunnel tests, we've achieved upwards of lift coefficients of 7 and 8. So you're talking about a fourfold increase. So there's a lot of benefit aerodynamically that could be obtained if you were able to actually design the system that could blow over the trailing edge and make this work. One of the problems that you see here is that you see how those streamlines are curving so much and going around the leading edge. We tend to get what's called flow separation. We'll get stall around the leading edge if we try to do that. If we try to use the circulation control too severely. So in order to prevent the flow from separating over the leading edge of the wing, we also put a little jet slot in the leading edge. That's what's shown right here in this schematic. We will energize the leading edge of the wing to prevent flow from separating, and that allows us to get up to those lift coefficients as high as 7 or 8. And the third technology, so we have circulation control, leading edge blowing. The third technology is over the wing powered lift. Now this is actually a picture of a NASA experimental airplane where what they did was they took the engine exhaust and they blew it over the top of the wing. And then you can see down here at the trailing edge of that wing, so here's the exhaust of the engine right there. At the trailing edge of the wing, that's a rounded Coanda surface. That's kind of like our dual radius flap, and they blew out that flap. So you take the engine exhaust, you accelerate over the wing, then you curve it around that Coanda surface. And that, again, has massive benefits as far as being able to increase the amount of lift. The problem is, especially with this case, is we have lots of scrubbing losses. We're losing efficiency because our engine exhaust is scrubbing against the top of the wings, and we can't turn it off. That's all throughout flight. And this airplane would be extremely fuel inefficient, extremely draggy. So what we came up with were the combination of these three technologies: the trailing edge, circulation control with a dual radius flap, the leading edge blowing, and then the ability to take our engine exhaust and deflect it downwards over the top of the wing such that it would be entrained or grabbed by that trailing edge flow and curved over so that we could get a combined lift increase. And we call that combined circulation control, or C3. And these are the three technologies that we were asked by NASA to design an experimental platform around those technologies such that we could investigate how well they perform. Now this platform, I'll show you a picture in a second, Mr. Chairman. We also designed a set of wings with Fowler flaps on them that so that what we could do is we could take the exact same airframe, same weight, same everything, pull off the wings with the circulation control technologies, put on wings with Fowler flaps, and do an exact or fairly close to exact experimental comparison between the two. Now, our contract with NASA was only to do the design for this. We were not obligated to build an aircraft. We realized early on that if we could leverage this contract and build an aircraft, that it would give us a leg up, that it would give us, having an actual aircraft sitting there would be much better than us having a design and wind tunnel results that said we think this will work. And this is where we went out into industry, and we actually went out to, we were introduced to the Georgia Center of Innovation, and we partnered with everyone you see there. Georgia Tech, as I've already told you, had designed the dual raised flap. They were our subcontractor on this, as was Boeing. NASA was our sponsor. But we had, in addition to that, we had Aerospace Fabricators of Georgia here. We had the Georgia Center of Innovation, which hooked us up with Middle Georgia College. We also had various other companies, Solid Concepts, who has a sales division here in Georgia. Aircraft Tooling Design Group, the Technology Research Development of NASA, Shaw Tooling, Aircraft Tooling Design Group. All of these companies stepped in and gave us a combined contribution of $250,000 in-kind or actual monetary contributions to help us actually build this aircraft. And this is as it stands right here. This is what we call our seated demonstrator UAV. And you can see in the right-hand corner, this is the version of the aircraft, the wings with the C3 technologies, and then this is the wing down the bottom left that has the Fowler flaps with the underslung engines. You can tell the difference. It's based on 11% scale 737, weighs about 180 pounds, and is powered by two JetCat turbine engines that generate 45 pounds of thrust apiece. And this shows those combined circulation control technologies again, and as they have been implemented in real life. Here we have on the left-hand side, this is our leading edge blowing. This where I have my mouse, this is our air plenum. This is where we pressurize the plenum, send pressurized air. That pressurized air then leaves out this very small jet slot right here and up over the leading edge of the upper surface of the wing. The right-hand side, this is our dual radius flap. Now, this system was designed by Georgia Tech, and then we did all the detailed design work to actually make it implemented. This is the only functioning dual radius flap. All other dual radius flaps that have been designed and tested in wind tunnel have been fixed fixtures. If they wanted to do deflections, various deflections, they had to pull off the fixture, get another one machined, and put it on. This is the only one that is actually functioning. And given that this jet slot is only is under 9/1000ths of an inch in height, these dual raised flaps had to be very, very accurate and precisely built. So in all, the mechanical aspect of designing this entire aircraft was very, very difficult. And you can see in the middle here, this is our hood system. We have a pneumatic actuator that deflects the hood downwards such that it'll deflect the engine exhaust down onto the upper surface of the wing. Inside the aircraft, there's a massive ducting system. We have two electric ducted fans. You can see in the bottom left-hand corner of the inlet here. These ducted fans compress the air and send the air out to the leading and trailing edge air pressure plenum so that the blowing can exit over the leading and trailing edges of the wings. Here's another picture of that ducting system. And these, I've just included some pictures here just to give you a reference of the actual complexity of the system that was designed. Again, here's the dual radius flaps and the structure that was designed to make that happen. Here are the leading edges of the wings. And you can see the aluminum lip along here. At the top of that aluminum lip is the jet slot where we send the compressed air. And here's a close-up view again of the hood. Yes. Oh, sorry. And just as a final, one of the things I wanted to just emphasize is that we heavily, our success in this was heavily helped by the Georgia Center of Innovation. We were able to do a lot of risk mitigation things such as extra wind tunnel testing because of research grants that we received, or the matching funds that we received from the Georgia Center of Innovation to work more with Georgia Tech. Middle Georgia College did all of the composite structures for us. They were absolutely invaluable. An incredible institution that is down in Eastman, Georgia. And this is from somebody who I've been around the aerospace industry. They are amazing. Rick Krantz and his crew down there, they are, Rick is a hidden jewel. And that relationship all was because of what we did with the Georgia Center of Innovation. Aerospace Fabricators of Georgia, they did all of the machine components of this aircraft for free. And they do a lot of work for Lockheed and for Boeing. And you can see all of these pieces laid out on the floor. And then, again, talk about Georgia Center of Innovation. They are largely responsible for that aircraft being there in our shop today, ready to fly. And that's all.
Sorry that we have to call it quit.
No, that's fine. I apologize for going over.
Oh, no, that's fine. I just have another meeting here shortly, so I will ask one question, and then I'll get out of here and you can answer questions other people may have. My one question is, okay, I get the concept of lift to get you off in a hurry, but you didn't say anything about stopping that little thing.
Well, the beauty is that we're, instead of landing at 110 knots or whatever, you're landing at 60 or 70. So your ability to stop is much higher with these technologies than others. And this will allow large aircraft to fly into urban or rural areas and hopefully reduce the airspace load that is on the national airspace. So.
Thank you for being with us this morning. I really appreciate that. And you too, Steve.
Well, feel free to stop by and see us sometime.
Thank you very much.
All right.
And the rest of you, if you have questions, go right ahead. I just have to go down the hall here. Thank you very much.
One question.
Yes.
Do you work with any of these groups that fly the remote control planes, or with children to get them interested in going into this as a field as you did as an education?
We have done some work with the Boy Scouts. We've done sponsored merit badge classes and had them come out and see the product or see our airplanes and talk about careers in the aerospace industry. The aviation merit badge in particular has a major component of that is having the Boy Scouts learn about other aviation careers other than being a pilot. And so that's something that we have participated in, but we haven't done. We're a five-person company. There's limited resources for a lot of that. But
since that was how you got your start, I wondered what you were doing.
I actually
for the younger generation.
I'm pretty heavily involved in. I'm an aviation merit badge counselor, so I do quite a bit because I do believe in that start, and that's really, that's what my career has become. As from 11-year-old kid, that's why I'm here, is because I started flying RC airplanes, and that grew my love of aviation, and I became a private pilot and went into to get my degree in mechanical and aerospace engineering, and everything I've done since then has been aviation oriented and led me to this point. So I try to excite those young people around me as much as possible with respect to aviation.
We have a small field and a group of maybe 50 to 100 people that are interested in my home county. And maybe I need to visit over there with them to see what they're
Where are you
they're
from
up
again?
to.
Where's your?
This would be Chattooga County,
Okay.
North Rome.
Yeah. Okay. Yeah, absolutely. It's I used to teach, when I was in graduate school, I used to teach what was called engineering state, where we'd get a bunch of high school kids that would come spend the week, and I would teach an aviation class where they would design a small balsa airplane, and we'd put it in the wind tunnel, and we'd teach them about stability. And my ambition someday would actually be to go back and teach junior high or high school physics or science, because I love that so much. The teaching is really my first love, and the problem is it's hard to support a family there. So that's where we are.
What is the primary purpose of
aircraft?
The primary purpose?
Yes, I'm just wondering.
I was laughing because she pushed the microphone in your face. I apologize.
Oh.
So, the primary purpose of the aircraft that we have is it's a technology evaluation platform. So the way we designed it is to be able to take any type of advanced aerodynamic technology, any type of weird wing, if you want to do blowing like we're doing right on our aircraft, or if you would like to do some type of, a hot topic right now is adaptive or morphing structures. We designed the platform such that it could accept those with relative ease. The primary purpose of it is to provide a platform that's large enough such that you can go out and you can flight test these technologies and gain enough. And the instrumentation, which I didn't talk about, is very high fidelity, high quality instrumentation that you can extract a lot of the flight performance data from your flight tests, and you can use that data to extrapolate up to how these technologies might perform on a full-scale aircraft. And this is of a lot of interest to companies like Lockheed or Boeing, who, when they're doing manned aircraft, if they have an advanced aerodynamic technology, they have to freeze that technology a year before they go flight test it on a manned aircraft. And that's it doesn't matter what they learn in that year, how they improve it. They might make the thing 100 times better than what it was back when they froze it, but they can't go flight test that because they had to freeze it a year ago. And now the technology that they might have to fly on that manned aircraft would be substandard to what they actually could fly. So they're looking at our platform as something that they could test multiple. They could go through that design and flight test propagation without incurring the cost and being able to learn the most they could out of that technology before they moved on to transitioning it to a manned program.
Yeah, let's just say, but for the short takeoff and landing, just to let you know about that, for example, if you have the ability to take off in a shorter distance and land at a slower speed, it greatly reduces the community noise around an airport. Also, the ability to land at a slower speed. If you're landing at 60 knots versus 110 knots, if you have any kind of incident or crash, a lot less energy that you have to dissipate, so it's much safer. It's a more survivable kind of event. So airplanes that can have this kind of technology on them will reduce noise and be safer to operate in the end.
Anything about that 737 a few Christmases ago that overran the runway, like in Chicago or somewhere near there? That those kind of things would be, that would be reduced, and that as the chairman asked about speed, generating more lift directly relates to reducing your speed, your flight speeds.
For the implications for economic development, I guess you'd say, in more rural areas of the state, are deal with this
Absolutely.
shorter landing and takeoff. I have Richard Russell Airport running
Mm-hmm.
the district, and of course, the state has been putting money into our regional airports occasionally.
Yeah.
But we would like to see more businesses and more cargo shipping from that airport, and so would all our United States.
That's something in particular in, say, cargo instance. You could have a centrally located cargo distribution center that might not be centrally located as far as close to a large airport, and you could take large cargo aircraft in and out of a smaller airport if, and you could reduce, as Steve said, the noise impact is very large because you can actually come in at a steeper approach and you can leave at a steeper angle, so the noise footprint is reduced, and disturbances there. There are a lot of really, with with this technology that we're trying to prove right now, there are a lot of different benefits, advantages that could be found if it could be used in a manner that was efficient and really provided gains over the conventional technologies. And that's what this platform is there to show, is whether or not it's to provide another data point to say, hey, you know what, circulation control is a good way to go, or it might show that it's not. And we're looking at, we're not blinded by that. We're trying to do an unbiased evaluation of the two. So. Well, we're glad to be here. We've been, I can't say enough how much the Georgia Center of Innovation has helped us now, and then even just 3 days ago on the phone with a large company who's looking at working with us, being able to tell them that we can essentially get wind tunnel tests at Georgia Tech for half off. We can get to this incredible composites facility down at Middle Georgia College. And their help, Georgia Center of Innovation has really become a huge part of my sales pitch, and to work here in the state of Georgia, it's helped us out as a very small company. It's made us have large company capabilities, and that's been a big deal. So, appreciate them. Thank you. Appreciate your time.